I'd like to introduce you to Dr. Serguei Beloussov, who of course is the Acronis Chief Executive Officer and the founder of the Schaffhausen Institute of Technology. Dr. Beloussov, I hand the floor over to you.
We believe that the world is converting to be digital, and digital workloads, the workloads which are bits and bytes, are actually zeros and ones, are very, very fragile. They could be easily destroyed. They could be easily copied, and so they need protection. There are these 5 challenges protecting digital workloads. There is potentially 500 billion digital workloads in 2030, based in 1 billion locations, so very, very complex to protect them. There is about 500 zettabytes of data, which is 10 times more data than there is today. Every autonomous car can generate 4 terabytes of data each day, 1 petabyte of data each year or more. Of course, security, industrialization of cybercrime, every digital workload can be attacked. Privacy, which we're learning to be a major concern, and the only way to actually be protected from the privacy standpoint is to have not only production platform, but also protection platform. And finally, especially with the current situation with COVID-19, we all have learned that without digital workload, we cannot operate. So basically today, everything we want to do, food, water, shelter, and air, well, perhaps air is available, but everything else is requiring digits to maintain and to support. And so it has to work at all times. So there's a great similarity between biological hazards and actually physical hazards. In case of biological hazards, COVID-19 have educated all the civilized world that there are these 5 aspects which need to be orchestrated and integrated fashion in order to be feeling safe. One is you need to have good prevention, such as social distancing, vaccination, good hygiene. Super important to have good detection. We all learned how important it is to have accessibility of tests in the early stages of this COVID-19. Response, to be able to actually cure and address the attack correctly, and it should not be too much for immune system either. Recovery and availability of actually hospital beds for that. And finally, forensic, to be able to do prevention, detection, and response. You have to understand what was going on with your body and with the population. This is extremely similar with computer viruses and computer digital attacks. You need to do things like vulnerability assessment, patch management. You need to do AI threat prevention, detection for detection. You need to be able to respond in real time better than afterwards. You need to be able to recover if disease actually was not able to be fended off with your immune system. And you need to understand what was happening with your digital infrastructure and digital workloads to be able to avoid having this happen again. We believe that our mission is to protect all data applications and systems. And to protect is not just related to security, it's also related to authenticity. You need to make sure that every data is original, and you need to be able to see where is a replica, where is original, and if original was modified. Who has access to your data? And access to your data allows to effectively control your free will. Accessibility, you have to be able to access your workload at all times, and you have to, of course, make sure that nothing gets lost and you can recover if something gets lost. And you need to do it in such ways that it's very easy, very cost efficient, secure. You don't lose control. There is no point protecting your privacy by losing privacy. And it needs to be extremely reliable, because effectively it is as important. You can live several minutes without air. You can live several days without water. You can live several weeks without food. But I don't know how long you can live without digital workloads today, and how long you would be able to live in the future. And for that, we have Acronis. Acronis is headquartered in Schaffhausen. There is a second headquarter in Singapore. I'm talking to you from Singapore today. We were founded in 2003 in Singapore. We moved into Switzerland and to Schaffhausen. So answering in advance, one of the questions, why in Schaffhausen? Because Acronis is in Schaffhausen. So I'm coming to Schaffhausen from actually 2006. We are a medium-sized company. We're growing very rapidly and we are accelerating. We are very pervasive. We are basically supporting 100% of all large businesses. And our expertise, artificial intelligence, software engineering, and application of artificial intelligence to business and to interesting areas like sports with our CyberFit program is what we do. Now, this is just a very small subset of human problems. If you think about the problems of the real world, they are much more broader, and that actually opens a huge opportunity for many, many different things. So we live in the world which is definitely suffering from diseases. We just seen it, and aging is one of the most important diseases today, which we don't really have an answer for. Environment and global warming, interestingly enough, we can see that it's sort of contradictory. With diseases, we were all quarantined, and so environment improved by much today. Social justice and poverty, very unfortunate reason for wars and violence. And of course, there are space and universe challenges, which if not addressed, humankind would not exist for many millions of years, maybe many thousands of years, but not much longer. Now, we know that based on modern science, effectively everything in the universe is a computer. So universe itself is a quantum computer. And so you can use computers to predict the universe. For example, no biotechnology today happens without computers, and the vaccine is actually made using computers before it is made using chemistry, before it is tested using biology and life sciences. And so it is definitely important to have better computers. What is actually computers? So computers are effectively Turing machines. This is one sort of very old computer. So the modern computers are equivalent to machines invented, abstract object invented by Alan Turing. What we use today is CPUs, graphic processing using GPUs, tensor processing using TPUs. All of these are actually Turing machines, and they could be modeled on a modern Turing machine. These computers are not perfect for some of the modern workloads. One of the main workloads which is coming our way is really deep learning and artificial intelligence. And so you have a number of designs to address it. Neuromorphic designs similar to human brain, the one on the left, 1 and 2. The one in the middle, which is slightly more complicated with elements of randomization, so more similar to human neurons. Photonic designs, which actually are much more power efficient and much more parallel versus silicon computers, also gives a promise to better deep learning engines. Now, ultimately, the modern silicon computers were governed by the Moore law, which was that number of transistors and resistors on a chip double every 24 months. And there are a number of limits with digital computers related to performance and throughput, power consumption, transistor size for silicon computers. And in general, there is these limits on the left, fundamental hard limits for digital computers. So there is Margolis and Levitin limit. And with the current progress with computation, we will grad to a hard limit in 75 years. There is Bremen limit, 60 years. There is organization which predicts that the silicon computers will stop accelerating in several years. One of the renowned experts in computer complexity, Scott Aronson, estimates that we will hit hard limits in digital computers in 25 years. So in 25 years, we will make computers which will no longer be significantly better per square, per cubical millimeter or cubical centimeter and per amount of power. And that's very sad, because there is this two very simple problems, and there is many other problems which we will not be able to solve on those computers. For example, many body problem, which allows us to predict behavior of matter and make new materials and so on and so forth. or even such a benign problem which is underlying all of the modern encryption, large integer prefactorization, and many other similar problems. So for that, there are some other computers which have been invented. So upcoming revolution is quantum computing and other possibilities. This is a picture of a Google record-breaking quantum computer as of October 2019. There is a misunderstanding that those computers are huge devices. They're not really. This is a sort of human-sized device. In fact, the computational unit is very small. This diagram describes the quantum supremacy. Basically, Google, for the first time in human history, been able to create a computer, quantum computer, which can solve the problem much faster than any classical computer, possibly. So within several seconds, something which will take thousands of years on a most powerful digital computer. So these are some of the designs of these computers. This is the designs which I personally think are most promising, called atoms. This is Misha Lukin group, my classmate in Harvard. Ion Traps, which is a commercial company, IonQ in Maryland. And then superconducting units in the industry, Google, IBM, and Rigetti. There are non-quantum computers which may be useful application for CERN, like black hole. Apparently, black hole allows the fastest, in terms of frequency computation, 10 in the power of 35. So for a simple super parallel computation, you might end up making a small black hole in CERN. And maybe that explains what happened to most of the alien civilizations. They reach a stage when they can produce small black holes, made a mistake, and got consumed into black hole. And of course, you can also think about advanced materials computers. For example, for storage, there is definitely a superior computational capacity of DNA-based computers. So this is one company, Catalog DNA, also from Cambridge, Massachusetts, producing super dense memory, which also can do some computation. Now, if we think about limits of computation, we should not forget that every human carries in their head most advanced computer of all. This is human brain. So if you think about human body, it's 200 billion atoms in the single DNA, which then generates 40 trillion cells in our body. So our body is quite large, which has 100 billion very large new cells, which are called neurons in our brain, which actually have 100 trillion connections, and it has only 10 watt power consumption and weighs only about 1.5 kilos, anywhere from 1 to 2 kilos. And in fact, the weight doesn't exactly correlate to the compute capacity. And in fact, today, if we think about the most amazing problem which stands in front of us in terms of science, we don't really understand how the brain works. It's not even clear that we know all the physics which is happening in the human brain. If we know all the physics around such powerful human knowledge generation devices, and in general, it is not clear how this can influence our science. Of course, there are people who think it's just a warm, wet Turing machine, but there are also people who think this is something beyond any digital computer. Now, with that, we can notice that besides solving such problems like creating an artificial human, there are more benign problems to be solved, like robots, sensors, and actuators are very, very, funny. If you think about birds and planes, planes are very awkward and very much unable to fly, believe it or not, but bats or owls can fly through a dark forest and squeeze between the branches as no drone in the next probably 30 or 50 years will be able to. And this Boston Robotics dog, which is running on the streets of Singapore in a very awkward way, noticing to humans to stay socially distant, can actually flip, but it flips in a very awkward way. If you compare the grace of this wonderful creation of human civilization into a normal dog, or less so a cat, it's completely crazy. And for that, you need better robots, sensors, and actuators. Photonic quantum repeaters, advanced materials, data storage, healthcare, all of this needs much better computers that we can afford today with silicon chips. One specific area, and I'm sure Artur will cover some of it today, is quantum internet. Today, we all sit at home and we all rely on digital information. This information are very easily copied, and so we can lose our privacy, very easily manipulated, so we can lose our security. The only way for us to really keep a secret is quantum communication and belief in the fact that humans have free will. And there is a wonderful article which is written by Artur and actually Renato Renner, the Swiss scientist who works for ETH, about how to keep a secret. And I recommend to read it. Artur may talk about it. The wonderful thing about the modern architectures is that once we create all these different computers, we don't need to choose. We can combine them into one of those clouds. And in fact, many of those clouds already combine CPU, TPU, and GPU. And some of them already added quantum computers. And I'm sure some of them will add advanced materials and other computers into sort of a fantasy mainframes. So here you have CPU, GPU, TPU, and this is one of the architectures, open source architectures. And you can have memristor, photonics, quantum computers, black holes, very special analog computers, and even brain power of humans attached to this machine. Now, in order to build the new computers on the right of that picture, you need new advanced materials, which is physics. You need to build new hardware, which is physics and engineering. Much so is engineering. You need new software to design them. Very much a progress of modern computers is related to the progress of software being able to design it. Think about modern silicon chip. It has 1.2 trillion transistors. If you talk about chips designed for artificial intelligence by Cerebras, and how can you put 1.2 trillion without a software together? It requires new operating systems completely different from what we have today, like macOS 10 on the slide with Steve Jobs, and new applications. And for that challenge, we decided to build a new institutions in Schaffhausen, which we believe is the best location for such institution, which is computers, physics, and business, focused on science, technology, and research, making unrestricted revenue streams and getting all sources of funding to be able to do science, technology, business, and education in those areas, specifically focused on cybersecurity, artificial intelligence, software engineering, and robotics and autonomous machine in case of computers, quantum technology and advanced materials, which are very specific fields of physics, and various business sciences related to science transformation. Reality is that to build even such a desired and simple conceptually device as autonomous car, which is happily running on the streets of Schaffhausen, but not extremely well, you need to have combination of all of these technologies. Ideally, autonomous cars drive much better than humans. We are very far from it today, which is evident from the RoboRace track which we've started. Now, in order to build it, first of all, we start from scratch in Schaffhausen. We created an alliances with top-notch institutions like Carnegie Mellon and National University of Singapore, and we built top-notch boards, strategic advisory board focused on scientists and scientific directions, headed by Konstantin Novoselov, who is a Nobel Prize winner in physics, expert in advanced materials based in National University of Singapore and University of Manchester. Nicolas Gézanne in University of Geneva, who is probably the most cited living physicist out of Switzerland. Artur Reckert, who will speak later today, who works in NUS, National University of Singapore, University of Oxford. Misha Lukin, author of one of the most promising design in quantum computers in Harvard University, and Mark Kamlet, who is a former provost of Carnegie Mellon. Representative board of directors, we believe the modern university and science, technology, and business clusters need to run like businesses. Good team already on the ground, running and doing work full-time. Strong industry board because we believe in deeply fundamental science with immediate application. And we also assembled group of friends of the university, which we call SIT Union, which is ready to help in a variety of ways, not necessarily full-time, but being involved, being able to give lectures, talk to you guys, and so on and so forth. Now, with that, I wanted to talk about our master programs. This year, we're only launching 2020 master program in computer science and software engineering. It is a sort of a standard description of the program as it is today. As we go next year, we will have 2 programs in quantum science, computer science, software engineering, quantum technology, and advanced materials. And as we move forward, we will also launch business sciences and science transformation programs. Again, this year, this is only computer science and software engineering program. And what is different about this program? Really 2 things. So first of all, we are focused on building leaders for small, medium, and large projects. Small, medium, and large projects are really what you will actually have in a modern science and in a modern business. It's very unlikely that you will have a project which will have one guy which will be able to code by himself for 10 years and have one product which will be amazing. It happens, but it's not common. And so typically for a startup, you should think about medium-sized project or large project. Medium size is 100 people, 10 years, 1,000 man years, 10 to 100 releases, requires group of leaders to lead this. And larger project is what we have in Acronis, for example, 1,000 people, 10 years, tens of thousands of man years, hundreds of releases. And so all of the people listed on the left side, all of these roles are needed. Some of the roles are quite unusual. For example, chief engineer and chief architect are 2 very different roles. For example, chief idea officer and chief technology officer are 2 very different roles as well. This year, we are focused on these 5 roles. Chief architect, very important role for software which have many releases over a long period of time. Chief product officer, very important for you to be able to make money and to satisfy your customers from your product. And again, your customers may be different scientists. Chief program officer, which is, of course, the person who describe the requirements deeply enough to be able to give it to engineers to code the product. Chief development officer, which is of course a person who need to understand architecture, the product, the program, and every aspect, but mostly manage people. And with modern software, very important role with chief security officer, which we as Acronis hope to convert to a new role of chief protection officer for every company. We will also touch with our program on chief science and chief design. The important thing is that nowhere in the world you really get education required to be leader. Instead, you are taught to be an engineer. You're taught to be a very solid beginner. Now, what is the difference? This is a sort of the list of areas which is different. First of all, in order to learn how to be a leader, you need to learn about leaders and need to be involved with leaders. And we believe we assembled very advanced group of people on our different boards who will all participate in connecting with our students to give them example, to give them mentorship, to give them teaching if they will teach. Then, of course, entrepreneurship, something which is very specific, starting the project and finishing it. It's, of course, important if you start your own business, but it's not even less important when you actually work in a large company. Then, of course, management. Management can be explained for computer scientists in the form of game theory, in the form of the program, and it's required for you to be able to succeed with your project. If you're a chief development officer, mostly what you do, you manage a team of leaders. Change management in software and in science, it's extremely important. It's about constant change. Science of people, what you really do about building any project is actually from 0 to the time in 10 years, you will, in a 1,000 people project, interview thousands of people, including internal people, including partners, including people who you would need to hire. And so you really need to understand people really well. Understanding how business is running, very, very important, because what we build today in science is connected to business, but definitely in technology, it makes no sense outside of the business. Our code needs to be made into product, which needs to be made into something you can market, which needs to be sold. And that all can be explained in the language of computer scientists to a computer scientist. And there is 2 specific areas of science, quantum informatics, which we believe will become very important with the presence of quantum computers, which are already available and will be more available over the coming years, and science of advanced materials, which is very much based on computers. And so with that, I conclude my speech. What you can do now, you can think of this wonderful 3 examples on the right. Alan Turing, Definitely took some time for him to be on the banknote and Bank of England, the founder, of course, in some ways of a Turing Award, the most prestigious award in computer science. John Bardeen, the guy who actually invented a lot of what we use today in our computation. The basics of our hardware is transistors. Hopefully, at some point, we will also use superconductors, will be very useful. And of course, Larry Page and Sergey Brin, which is the ultimate examples of super successful graduates of super successful master program in Stanford. So what you can do now, you can actually protect yourself with Acronis cyber protection, which will help the university indirectly. You can join us as a researcher or faculty. We are looking for people. We are looking for investors. We are looking for people who want to support us. And of course, we are looking for students. So you can become as famous as Alan Turing. You can get two Nobel Prizes like John Bardeen. And of course, hopefully you can build startup, maybe not as successful as Google, but almost. Thank you.